So we actually started ODEs earlier. There's about 5 or 6 people absent today. It's not a big class anyways. Ordinary differential equations. We did these earlier, where you had dy dx equal to some function. We did the antiderivatives and everything. We are stepping it up. Big time stepping it up. Okay, these are much more complicated in your solutions, in your steps to solve them. We didn't have any y's involved in doing the antiderivatives. We will have them involved in what we're doing today. It's not a difficult process from the standpoint of it's step by step. Step number 1, separate the variables. Y's and dy's on one side, x's and dx's on the other side. And you want to have the y side as simple as possible. So if you have other numbers involved, other things other than just x and y, you want to have as simple a y as you can. So if you have like 2xy, you leave the 2x alone. You don't take the 2 and move it with the y. You just move the y only. Okay, you move the y only as much as possible. Integrate, in other words, antiderivatives, plus c. Do not forget the plus c. Solve for c using the initial condition. You're given an xy that this function passes through. Solve for c. And then your last step is solve for y. Sometimes it's extremely difficult to solve for y equals. None of the ones that I give you. I've seen a couple of the homework problems can be really nasty, but most part they're solvable for y to get y equals. Sometimes they're complex, but that's the goal you want to have. You want to get y equals in the end. But you follow these steps, it's not too bad. Okay? And we have done this. We're just stepping up from what we did at the beginning of this chapter. By the way, I have 2 people who still need to make up the quiz. Yeah, get that as soon as possible. I want to give them back. Scores were good, so I just want to make sure you get them back so that way people can talk about them. Okay, so consider the differential equation dy dx equals 3y. Find the solution y equals f of x to the differential equation, satisfying the initial condition f of 0 equals 1. Okay. So, dy dx equals 3y. First step, y's and dy's on one side, x's and dx's on the other side. I don't have any x's, so I just have to move the dx to the other side. But I do have to move the y. Leave the 3 on the dx side. Leave the 3 alone. Just move the y over by itself. So to do this, divide both sides by y. And then multiply both sides by dx. So you end up with 1 over y dy equals 3 dx, and let's pause for. Okay, so let's pick up. So you get 1 over y dy equals 3 dx. Integrate. Take the antiderivatives, and this is where it can get fun. Okay. Actually, I think the separation of the variables is the hardest part. That's your first step. That can be difficult. There's a couple of tricky ones we're going to do later. But 1 over y. What's the antiderivative of 1 over y? ln of y, natural log of y. So you get the natural log of y equals the antiderivative of 3 would be 3x, and then plus c. Now, you need to plug in your initial condition and solve for c. You can solve for y first and then solve for c. I'm going to tell you right now, it's a whole lot easier to do it at this point. Step aside from that, plug in your 0 for x and 1 for y, and solve for c. It is so much easier to do at this point than it is to do later. You can do it at any point, but it's much easier to do now. So if I take this, go over to the side, so I have the natural log of 1 is equal to 3 times 0 plus c. What is the natural log of 1? 0. So what is C? 0. That's nice. Ooh, I love it when C equals 0 because then I can just ignore it. Okay? So much easier when that happens. So this is now 0. I have the natural log of y is equal to 3x. But here's my problem. What do I want to do? I want to find the solution y equals. I don't have y equals. I have the natural log of y equals. So what do I need to do? What's the inverse of the natural log? E to the whatever. Raise both sides to the e power. E to ln of y, e to the 3x. So I get y equals e to the 3x. That's my solution. Okay. Now, there's one thing I didn't do that we normally do when we take antiderivatives. What didn't I do? Particularly the antiderivative of the natural log. No, I didn't. Actually, no, I'm not wearing my absolute value shirt. I thought I was wearing my absolute value shirt today. My bad. Yeah, absolute value of y. There's a reason. I have my initial condition. My initial condition will tell me whether my final y is positive or negative. Because what I have to do is go back, and this is where part B, find the domain and range of the function found in part A. My original condition determines that domain and range. That determines my possibilities. Because if it was equal to -1, then my graph would be below the x-axis. If I ever graph this one out as it stands here, it looks like that, something like that. If I had it equal to -1, if f of 0 was -1, my graph would be there. That would be my particular solution with the underneath. If you do a slope field of the original graph, it covers the whole gamut, above and below. Because it is possible to have the slope field be a negative underneath, because we're doing the absolute values. So we could have possibly our original function would be underneath. This one tells me, this right here tells me whether I have this or this at this point with the y. So my domain and range, my domain is all reals, because I can plug anything in for x, right? I can take e to any power. That's good. But my range, y is greater than 0. And that's strictly because of my original condition that I have. If I had different numbers from my original condition, my domain and range, my range would still be the same. My range would still be all real numbers. My domain, my range might be less than 0 based on my initial condition. Okay, this one, my graph is above the x-axis. Everything's above the x-axis. It's fine. If my initial condition had a graph that was below the x-axis originally, then my range would be everything less than 0. Okay, so your initial condition is important for this. I have seen that as a question on the AP test. They throw it in there. I get the feeling they throw this last question in here when they need one more point. When they've done everything else, they've done the rest of the scoring, and they've got 8 out of the 9 points required, that's when they'll throw in to give you that 9th points. They have 9 total points for their question. Because all 3 response questions all worth 9 points. And I get the feeling that they throw this one in there, not because they really want to know if you can do how to do it, but we really need to have one more point. And they do that. I get the feeling that they do that. Questions so far? Okay. Same idea. Consider the differential equation dy dx equals 1 plus y over x. Find a general solution to the differential equation above. Still want to get y equals, but a general solution means that we don't solve for c. So we don't have an initial condition. You will see this once in a while. This is fairly rare that you see it without an initial condition. You usually have those when you're solving these. We're looking to see if we can come up with an equation, just a general equation, solve for c if we need to at a later date. So you will not solve for c, but c will be part of your answer as we're going through this. You still want to get y equals at the end if you can. Sometimes you can't. You want to do that if you can. So, dy dx equals 1 plus y over x. So, to get the 1 plus y to the other side, what do I have to do? I have to divide or multiply by 1 plus y on each side, right? So those cancel. Multiply both sides by dx. I get 1 over 1 plus y dy equals 1 over x dx. Separate the variables. Dy is y dy, x dx. First step. Second step, antiderivatives. What is the antiderivative of 1 over 1 plus y? Yeah, natural log of, because it's no powers, it's no roots. If I had a square root around the denominator, I'd do a u sub or just change it to 1/2 power. If I had something squared, it's different. It's 1 over y plus 1 by itself. Yeah, it's natural log of y plus 1. I'm sorry, 1 plus y, y plus 1. Same thing, but you kind of want to keep it. Equals the natural log of x. And I do have to put the absolute values about these because I don't know. And then don't forget your plus c. Yeah, most equations, most problems, you would be given an initial condition to plug in, solve for c at this point. Don't have that here. I have to solve for y. This is where it can get kind of tricky. So once again, how do I get rid of the natural log? Yeah, raise both sides to the e power. So I have e here and e of that whole thing. Well, this side's easy. That ends up being 1 plus y equals e to the x times e to the c. Because what are the rules of log? What are the rules of exponents? Two things added, powers multiplied, right? Two things multiplied, you have the powers. So if I have, or sorry, that's not e to the x. That's e to the natural log of x, e to the c. I kind of got ahead of myself on this step. So do you see where I got from one to the other? Because what are your rules of exponents? E to the natural log of x times e to the c. What do you do to the powers? You add them, right? Which means you can also separate them. Your rules of exponents and your rules of logarithms go both directions. You absolutely must remember that. I cannot tell you how important it is to remember that this goes to this just the same way as this goes to that. It goes both directions. You absolutely have to have that down. Otherwise, it makes it really hard to solve. From here, it's actually not that bad. I have 1 plus y equals e to the natural log of x is x. E to the c is some constant, right? Generally speaking, you would use c for it. We will use c for all our constants. One of the rules that we will have, or one of the few things that generally is done, is you have e to the c. Normally, what do I say? What is c plus anything? It's still c, right? Some constant we don't know. E to a constant we don't know is still a constant we don't know. Generally, for some reason, they rewrite e to the c as a. This is something that somebody adopted at some point. Why you can't just keep calling it c for forever, I don't know. You could, if you put cx there, instead of ax there, it would mean the same thing. It's still a constant we don't know. For some reason, if they have e to the c, they don't rewrite it as c, they rewrite it as a. Every time we've ever done c, you add a constant or adjust it, multiply it times something. What's 2 times c? It's still c because it's still a constant we don't know. What is e to a constant we don't know? It's still a constant we don't know. But for some reason, they don't write it as c anymore. They like to write it as a. I don't know why.
Do you know if AP has a preference to which?
No, either one would be fine. You could put down almost any letter as a constant. They really probably wouldn't care as long as you're using some constant. Plus C is your standard. You want to stick with that as much as possible. If you used C there, or K, or D, or B, or anything, that would be fine. If you use C again instead of A, that would be fine. I'm not going to mark you down for it either. I'm just showing you what is typically done. Most textbooks do it this way. AP tends to do it this way on their answer keys. Does it really matter? No, as long as it's some constant.
Would you need to keep writing the absolute value of y?
Good question. Absolute value of y plus 1. That's an excellent question. One that I'm not real sure of, because it's hard to say what to do. Once again, if we had a domain and range, we had the original problem, we should do that. It should still be the absolute value of x at this point. It's very good to point that out. Problem is we can't solve for y if we don't have the absolute value there anymore. Does that make sense? Because you want to get y by itself. So it's kind of, if you're doing absolute value of y, the absolute values here, and here, and here, then you're done at this point. If you don't have your absolute values, then you can solve for y. And you get y equals ax minus 1, because you subtract 1 from both sides. Really hard to kind of judge. It's one of those ones that's really iffy. If I gave you something like this, I'd take either one of them. I really would. AP is not going to stick you in a place where you have to make that decision. They don't do that. I've seen them do other things that are not quite so nice. This is one that they're not going to force you to make a decision. They're going to give you a constant to do that. If they don't, this would be a multiple choice question, and then you would have the choice. And you would see the absolute value would be part of all the answers or part of none of the answers. It'd either be there or wouldn't be there at all. It wouldn't be with or without. Does that make sense? Yeah. So that's a good question, very good question. And it is. There's some gray areas in what you do. Okay. Consider the differential equation dy dx equals 3x squared over e to the 2y. Taken from the AP free response. This is a direct question from AP. Find the solution y equals f of x to the differential equation satisfying f of 0 equals 1/2. See it? Most of you are on the right track, but there are a few details here and there. So dy dx equals 3x squared, e to the 2y. Multiply both sides by dx and e to the 2y. So you get e to the 2y dy is equal to 3x squared dx. And most of you got the antiderivatives just fine. This should be 1/2 e to the 2y equals x cubed plus c. So I plug in 0 for x and 1/2 for y. So I put in 0 for x. This goes away, and I get just c. So what does the other side equal? C equals whatever's on the other side, right? I put in 1/2 here. I get e to the first, which is e. So then c equals e over 2. Or 1/2 e, if that's what you want to put it as. Either way would work. So I go back up to here, and I end up with 1/2 e to the 2y equals x cubed plus e to the, e over 2. A lot of you got to here just fine. Now solving for y, you want to take the natural log of both sides. But before you do that, you want e to the 2y by itself first. Get rid of the 1/2 in front. Multiply everything times 2. E to the 2y equals 2x cubed plus e. All right, multiply everything times 2. Take the natural log of both sides. And it's the natural log of the whole thing. So I end up with 2y equals the natural log of 2x cubed times the natural log of e, right? Because it's the rules of logarithms work the same way. What's the natural log of e? 1. Because the natural logarithm of two things that are added is the natural log of each item. Multiply. Right? Yeah, that's the rules of logarithm. Is that right? Is the rules of logarithm, are they correct or not? No. I got to get this one right because I'm trying to remember. Yeah, it's not. It's still e. The e's still there. You're right. You know, if this had been after Friday's lesson, I'd be fine because I'm doing the rules of logarithms with my Algebra 2 kids on Friday. And I'd have it down. I would have remembered it. No, this is not. It's still just the natural log plus e. You can't do that. You can't distribute. It doesn't combine because the natural log of xy is the natural log of x plus the natural log of y, not the natural log of x plus y. Does that make sense? This is the rule. I was not following the rule, was I? Because it's not the natural log of x plus y. Yeah, I screwed that one up. My bad. It's not like it's the first time I've screwed up in here. Multiply both sides by 1/2. You get y equals 1/2 natural log of 2x cubed plus e. And then the question I have is, do I have to worry about being an absolute value for the natural logs or not? Because we're not allowed to take the natural log of 0. We're not allowed to take the natural log of a negative number, right? Well, what's my domain? And this is where I have down here, it's kind of hidden. Domain and range is the function found in part A. This goes back to my original condition. X is 0, y is 1/2, is that right? Yeah. So if I were to do, what does the natural log function look like? That's what the natural log function looks like. That's the typical natural log, right? So because it goes through 0, 1/2, that is because I have other stuff in there. It just shifts it over. That's all it's done. And it's shifted over by 1/2. So my range is what's going to make this 0. I have to be larger than that. Because I'm not allowed to take the natural log of 0 or a negative number. So what I have to do is I have to take 2x cubed plus e, set it equal to 0. And I got to figure out where is that 0. That's the limit of my x's. X can't be smaller than that value. I'm not allowed to take the natural log of something equal to 0 or a negative. I have to solve that. Not a problem. Subtract e. 2x cubed equals negative e. Divide by 2. X cubed equals negative e over 2. So x equals the cube root of negative e over 2. That will give me 0 for my natural log. I am not allowed to take the natural log of 0, so x needs to be larger than that. That's my domain. My range will be all real numbers. If you look at the graph of natural log, your range is always all real numbers. It's your domain that you got to worry about. Okay. So my domain x is greater than the cube root of negative e over 2. And we're allowed to have a negative inside the cube root, right? How are we doing so far? Clear as mud? Okay. So, same idea. There's a problem. I don't have any x's in there. Okay, to get y by itself, add 2y to both sides, right? What do you get when you add 2y to both sides? If I add 2y to both sides, I get dy dx plus 2y equals negative 6. I can't get y dy's because when I multiply through by dx, I still have this times dx here, don't I? You want a hint? Oh, come on. There we go. Factor it first. Factor your differential equation before you split the variables, before you split the y's to y's. Factor it first. This is a tricky one. Okay, let's work this one. So you'll notice I already did the factoring. Pull out the greatest common factor. Now I have two things that are being multiplied. Now I can split it. You have to have things that are being multiplied. You have to have your y's times x's. You can't split it otherwise. So from here, I split it, divide by y plus 3. I have 1 over y plus 3. dy is equal to negative 2 dx. So I end up with the natural log of the absolute value of y plus 3 equals negative 2x plus c. Plug in the initial condition. When x is 1, y is negative 10. Okay, this is one where we got an interesting thing going on here, don't we? When x is 1, y is negative 10. Okay, so I end up with the natural log of negative 10 plus 3, absolute value of that equals negative 2 plus c. So c equals 2 plus the natural log of the absolute value of 7. Right? Do not give me decimals. Do not do that. Leave it at that point. So c equals 2 plus the natural log of the absolute. Stupid balloons. Absolute value of 7. That's what c is. It's not pretty. It's not going to be pretty. Life's not pretty. Always. Okay. So I have to go back to my original problem. Plug the c in there. So I get the natural log of the absolute value of y plus 3 equals negative 2 plus 2. Sorry, negative 2x plus 2 natural log. Negative 2x plus 2 plus the natural log of the absolute value of 7. How do I get rid of the natural log? E. So I do both sides to the power of e. Absolute value of y plus 3 equals. Now I take, because I can do this, they're all being multiplied. I have e to the negative 2x, e squared, e to the natural log of the absolute value of 7. Well, the absolute value of 7 is what? 7. We know that. So e to the natural log of 7 is 7. So if I rearrange this to make it look pretty, there's really not a lot I can do. Is I don't really want to take this and separate it out, but bring the 7 out in front. So I get 7e to the 2 minus 2x. That's about as good looking as you want to get. I could write e squared and e to the negative 2x, and that's 7e squared e to the negative 2x. But then I got e to some power and e to some power, both of them the same thing. It should be 1e to 1 power, right? That's going to make it look as good as it can. Now we got to solve for y, and this is where it can get tricky. We have to look at our initial condition about losing the absolute value or not. Y to the 1 equals negative 10. If I put 1 in here, I get 7, right? If I put 1 in here for x, I get 7. So I get absolute value of y plus 3 equals 7. But y has got to be negative 10. So I've got to screw with this thing to make sure that I'm getting the right answer out of it when I plug in y. So I can do the absolute value or I can do the opposite of absolute value. If I put here and I get 7, I have, negative 10 for y. How can I cope with that? Because my answer is negative, it's really, really actually very easy. Would that work to give me my answer? And what you have to do is just mess with your pluses and minuses and see what works. If I take this and make it negative y minus 3 equals 7e to the 2 minus 2x. What?
So when you do plug in the 1 for the x,
yeah.
That way you get negative 1 on top.
No, you get 2 minus 2. What is 2 minus 2?
Oh.
No. It's you get 2 minus 2, which is 0. E to the 0 is 1. Okay. Add 3 to both sides. Negative y equals 7e to the 2 minus 2x plus 3. If I were to plug in 1 here, I get 10 equals negative y. If y is negative 10, is that going to work? Yeah. But I don't want negative y, and I'm running out of room because I have the stupid bar across the bottom. Y equals, put the negative to the other side, negative 7e to the 2 minus 2x minus 3. You just have to go back to your initial condition. What's going to work? Is it going to work with y plus 3, or is it going to work with the opposite of y plus 3? At some point when you're solving for y, you need to make that decision. And you pick one and go with it. And then you try your answer. See if you get what's supposed to work. If I plug in 0 here, do I get negative 10? Yeah. If I plugged in 0 and I was supposed to get positive 10, I would just have y plus 3 here. Your initial condition tells you whether you're using y plus 3 or the opposite of y plus 3 when you drop the absolute value bars to solve for y. Your initial condition tells you everything about that. Okay, that's why it's important. Okay. Please note, this was the scoring rubric for a portion of an AP question, last year that required solving an ODE with a given condition. It's 5 points. This is the largest single type of problem AP asks. It's worth the most points of any single one object. Okay, because they're always, their free response questions are, here's this information, A, B, C, or D, and or D. This is the biggest, largest single point portion of any free response question is 5 points. That's a big one. You get 1 point for separating the variables. You get 1 point for y dy on one side, x dx on the other side. You get 2 points for the antiderivatives. 1 for your y antiderivatives, 1 for your x antiderivatives. And you get 1 point each if you do them correctly, obviously. You get 1 point for plus c, that's the constant of integration, that's what we mean by that. And plugging in the initial condition, you get 1 point for getting y equals as your final answer. Please note these right here. These are the ones that kill a lot of people. When we do practice tests, I've seen this screw people up. Maximum of 3 possible points. A maximum of 3 points if you forget to put plus c. You don't put plus c, you can't get the last 2 points no matter what. You can get y equals. You can get y equals. Doesn't matter if it's the correct y equals because c ended up being 0. It doesn't matter. You don't put plus c, you cannot get those last 2 points. And a lot of the AP test is getting as many easy points as you can. Literally, this point here is putting plus c and plugging in the original conditions for x and y. Whatever number they give you for x, you put it in for x. Whatever number they give you for y, you plug it in for y. Even if you don't get what c is, you still get a point for plugging in x and y. You still get a point for that. If you screw up the antiderivatives, you can still sometimes get the point for plus c and the point for plugging in the point for plus c and plugging in the x and y. Even if you screw these up, depending upon how bad you screw them up. Really, they'll say like, well, there's no way that's even close to what the antiderivative is supposed to be. We're not giving any partial credit. We're not letting you use your bad answer because your answer is so bad, we're not going to use that. But let's say it's a polynomial and you got the power screwed up. That's not that big a deal. But if it's a polynomial and you tell me the antiderivative is a natural log, yeah, they're not going to give you credit for that at all. Okay. Notice, if you do not separate the x's and y's, you do not get anything. You don't do that first step right, they don't even look at the rest of it. They don't. And it's one of the few times, this is one of the few times where they don't do something like that. If you can do what we've been working with here today, it's a big part of AP. Points are important. And I know when we start doing the practice questions, you guys are going to freak out because it's a 9-point question and you're getting 3 points. Oh crap, I'm an idiot. I get 3 out of 9. I get 3 out of 9. I get 3 out of 9. Until you start looking at the average scores. Oh, the average score was 2.9 on this one. Oh, the average score on this one was 3.5. Once in a while, you see an average score at about 4.5. That's about the highest average score I've ever seen out of 9. So if you're getting 50%, you're doing really good. Part of the test is getting points. And you can't get the points if you don't do partial credit, if you don't make the effort to solve the problems. And just separating the variables gets you going down that right track. When I grade this test coming up at the end of this chapter, which 1 week from today, I'm going to grade this question basically just like this. My difference is I'll give you a point for trying. They don't give you any points for trying. If the answers aren't right, they don't give you any points. I give you a point for trying. So it'll be worth 6 points, not 5. But generally speaking, that's usually what I do. I start grading closer and closer to AP as we go along. But the expectations are headed in that direction. Plus, it's also easier to do it when we're near the end. Because then I can give you questions that are just like what they asked. So it's very hard to do that at the beginning of the class. Okay. Questions? Okay.